Okay, hello, welcome back, and I hope you all had a wonderful holiday break. So this is the last but 1 week uh, of this semester, and I'm gonna for in this lecture we are gonna cover the mixture Gaussian model, EM method, and in the next lecture this week, Thursday, uh, I think I'm gonna give topic on the generative models, which is quite related to the mixture Gaussian models, and also the hot topic such as generative adversarial models, the generative adversarial network, which is the so-called GAN models. I will also cover a bit of that. All right, so let's look at this mixture Gaussian model. So I list this mixture of Gaussian and the EM method into this chapter with the other clustering algorithms because first of all, the mixture Gaussian model is indeed used as a clustering algorithm. And there's a major difference. The main reason that I listed as the last type of algorithm that we're going to cover is that it is different from the k-means, the hierarchical clustering, the density-based clustering, because it does not assign a hard cluster labels to the data points, but rather it assumes that one data point can actually belong to multiple clusters. With each cluster, there can be a probability that indicates the likelihood that this data point is from that cluster as opposed to the other clusters. Okay, so it's a more of a kind of a soft assignment of clusters. So there's a more, it allows for more flexibility in terms of uh, the in terms of which clusters that each data point should belong to. So there could be more than multiple clusters. Okay. So yeah, let's look at the motivation. So in k-means, so we use k-means as a comparison here. So k-means make hard assignments. So each data point must belong to one of the clusters from 1 to k, right? And sometimes one data point can actually, it's really hard to tell which one it belongs to. And there could be overlaps between clusters. For example, in this group of data points, if we think of that it is the result of two overlapping clusters, then it also makes sense. So those data points that in the intersection of this within this blue and orange ellipse, these data points in the middle, they are kind of uh, there's overlap between the clusters. So they belong to both clusters. So a k-means would not be the most convenient way or the most reasonable way to say obtain the cluster information for these overlaps. Okay, so a more reasonable way is actually to allow for the to allow those data points to belong to different clusters by assigning each data point a probability or a set of probabilities, which shows that, okay, for example, these data points may have 60% belonging to the orange or 50% belong to uh, the blue one. And actually, we can also think of the probabilities assigned as the weights to one data point. Like a data point becomes a mixture or a blend of two distributions. It is a mixture of 50% of the orange distribution and 50% of the blue distribution. Okay, so that the nature of data points are better understood. All right, so a little bit about the motivation. And in order to achieve these assignments of probabilities, we need to use um, the Gaussian models. Okay, so we'll first do some reviews about what a Gaussian model is, what a Gaussian distribution. Okay, for Gaussian distribution, we also use the name normal distribution. So it's actually, we're referring to the same concept here. So we look at the one-dimensional, which is also called the univariate Gaussian model. And in mathematics, we can represent this one-dimensional Gaussian with this capital letter N, which is for normal, and with the Greek letter mu and the sigma. Okay, so the mu is for the mean values of the distribution, and the sigma is for the variance or standard deviation. Okay, so we can use the mu. Actually, the mu and the sigma here indicates the probability density function or PDF function. Okay, based on which takes inputs a continuous number x as inputs. Okay, so this PDF function is in this mathematical form, and it describes the shape of a typical one-dimensional normal distribution or Gaussian distribution. So the mu is here, this is the mean value, and the sigma is here. And the sigma is also outside the exponential function. So this function, if you look at its shape, it's a bell shape, okay? And the height and the width is, and the position, the central position, the position of the central points is determined by the mu and the sigmas, okay? So mu is in the middle. And what this function can be used for is to compute the probabilities of the inputs is above or below a certain threshold. For example, if we want to know the probability that a random variable x is lower than mu, and of course, we assume that this x is randomly drawn from this distribution. So the probability that a randomly drawn value is lower than the mean value is actually the results of the integration uh, on top of the PDF function, which from the range of within the range from the negative infinity to the mu. So which gives us the result of 0.5. Okay, so this is a very common usage of the PDF function in computing the probability of certain values of the random variables. Okay, so we can also define a customer range within this PDF function, and the area under this PDF function describes the probability that a randomly drawn variable falls into this range. Okay, so for instance, the area under this range indicated by the green color is actually the probability that um, a randomly drawn variable is smaller than the mean values minus one standard deviation. Okay, and it's actually the same value as this range on the right wing. Okay, which is the probability of the random variable is greater than mean values plus one standard deviation. Okay, so these are just simple examples showing how the um, the PDF functions can be used in various types of computations. Okay, all right. So Gaussian distribution is ubiquitous. We can find it almost everywhere in statistics. So in biology, usually speaking, the logarithm values of a lot of variables are in a more or less a normal distribution. And um, many other variables listed here, like the price, stock market price, and also in language, the frequency of words, the length of sentences. After we take the logarithm of them, they all present some distributions, which is very close to Gaussian distribution or normal distribution. Okay, so showing these examples, the purpose is to show that Gaussian is a very commonly observed distribution, and that's also why we can use Gaussian models to describe our data, right? Because it is very ubiquitous, and many of the quantities that of our interest are can actually um, be described by a Gaussian distribution. Okay, so now let's further look at what a Gaussian model is. Okay, so we can use the mu and sigma to define a Gaussian distribution, as we have seen in the previous example. All right, so now a Gaussian model uses mu and sigma as the parameters to define a model. Okay, so a parameter is unknown at the beginning, right? Parameter is something that we want to obtain through training, through observing huge amount of data, and then we can from these data we can have some estimates for the parameters mu and sigma. Okay, so the difference is that if it's a model, if it's a Gaussian model that we want to estimate, then the mu and sigmas are not known at the beginning. These are unknown variables. So if we want to estimate such a Gaussian model, then we need to assume that each data point is randomly drawn from the distribution. Okay, because the mu and sigma are unknown, so which means they can be learned from the data. And our job here, our goal here is to find the parameters, find the target mu and sigmas that best fit the data. Okay, so from this perspective, it is not very different from the other supervised learning paradigms we are familiar with, like the linear regression, logistic regression models. And we also have a bunch of thetas to fit. And here in the Gaussian model, the thetas are represented with different names with mu's and sigmas, but they are no more than not very different from other than the sigmas in other models. They're just models of the parameters within the model. Okay, so in terms of best fit, we need to answer what is the best fit. Then that means we need to define the cost function, right? We need to define the distance between a prediction and the ground truth label. Okay, so in this case of Gaussian model, we will use the well-known technique called maximum likelihood estimation. Okay, so we have mentioned this, we have touched this before in logistic regression model when we provide a probabilistic view of logistic regression, right? We also use the likelihood of the data points. So which is so the concept here is not something that we are not totally familiar with. Okay. All right. So let's look at further proceed on to the construction of this maximum likelihood estimation. Okay. So we use a very concrete example using the classification of fish between salmon and the tuna fish. Okay. So the data is the weight of a salmon fish. And our assumption is that the weight is from a Gaussian distribution. Okay. All right. So I want to correct what I previously said. This is not a classification task yet. So our task is to simply to estimate the mu and the sigmas, and we want to find the best estimates for mu and sigma that best fits the existing data sets, which is the weight of the salmon fish, which is just one quantity. Okay, so given a bunch of weights, we may have observed if we plot it along this x-axis, we may have a visualization like this, right? So the task is to find the mu and sigma that best fits the observed data. So what should be the central point, and what shape should it be, so that the PDF function best fits the data. Okay. So let's do this with maximum likelihood estimation. Then given all the data points, we need to fit a Gaussian model. So take each data point out, like take one data point out, which is xi. Then the PDF, the value of the PDF function at the point xi is defined like this, right? It is given by the definition of Gaussian distributions, right? So the theta here actually refers to the mu and sigmas, okay? So the probability density function of xi given theta is described by this mathematical formula, right? Which is an exponential function, all right? So it's the meaning of it is how likely it is to observe that data points xi given the parameters theta, okay? So, and we also assume all data points are independent. So that means observing one data point, say xi, is independent on does not depend on the observation on xj or xk plus one or any other data points. So that means we can also think of the likelihood of the total data sets is simply the products of the likelihood of all the individual data points. Because they are independent observations, all the data points are independent. So we can use the products of the likelihoods of all the data points as the likelihood for the whole data sets, right? So now we can use the product, the operator to write down the likelihood of the whole data set, which is capitalized X. Okay, so this is a uppercase capitalized X as the product of all the data points within the data sets. Okay, then we say a good estimation of theta will maximize this likelihood of the data of the total data sets. Okay, so now we have something. We have a more clearly defined goal that we want to maximize, which is the likelihood of the data. Okay, now let's look at the next step. Right? So we use the L letter to indicate the likelihood function, right? Which is the product of all individual likelihoods. Then it is an exponential function. So mathematically, we can take the logarithm of it, and the logarithm does not change uh, the property of a function in terms of whether it is increasing or decreasing, monotonically increasing or decreasing, right? So we can apply a log function to compute the log likelihood, which is double L, right? So taking the log function is very convenient because it cancels the exponential term, right? And also it converts the product into a summation, right? The logarithm of a product is the will be the summation of the log applied to each item of that product, right? So basically apply log to each exponential function, and which will gives us a very convenient term like this. Okay, so if you look at this term, this is no more than a constant, right? The logarithm of 2 pi. And here there's a variable involved. The sigma is here. And also the summation of these squares, right? So which is the difference between the xi to each mu, so which is not changed from here, right? It's directly moved down to here because we take the logarithm of the exponential function, which doesn't change the index term at all. And this is a much more friendly form in terms of uh, as a target function or as a cost function. All right. So now the goal is to find the mu's and sigmas that maximize this log likelihood function. All right. Right. So this is a very typical quadratic function that we can easily take the derivative of, right? Because this is the log likelihood function, and we can simply take the derivative of this log likelihood with respect to the two variables, mu and sigma. If it's with respect to mu, right, then the only term left is this one, because the other two terms has nothing to do with mu, so they can be viewed as constants, right? So we can apply the rules of computing derivatives, which is a which becomes a very easy term, right? It's the summation of all the data points minus mu times m times mu, and mu is simply the mean values, right? So, and the likelihood of sigma, which is also easy to compute, um, which, well, honestly, it may be a little bit trickier because there's two terms involved. Here's the log term, and here the um, polynomial term, right? But we know that the coefficient here is -2, so here it becomes -3 as the principle of taking derivatives. So anyway, these are still polynomial terms, and by making these uh, derivatives to be 0, we can compute the maximum points, right? So making these two derivative to 0, we can easily compute that the mu is estimated by this way, and the sigma is estimated by this way. So from at this moment, we may find that, okay, wow, this is a very intuitive solution, right? A good estimate for the mean mu is simply the arithmetic average values, right? We just take the summation of all data points and divide it by m, which is the total number of data points. Well, this is very self-explanatory, right? And the sigma, it is just by first computing the mu, and then we use the difference between the data points and the mu, and compute the square and sum up all the square values and all the squares divided by m and take the square roots, which is the definition of the standard deviation, right? So we actually simply need to compute the mean of the data, which is the sample mean, right? We don't in theory we don't have access to the whole sets of all the possible data points. All we have is a sample, and we have a variance, the sample variance. Okay, so these may remind you of what you learned in statistics classes, right? So when mu is estimated with the sample means, then we actually need to change the derivatives, the denominator here from m to m minus 1, so that the estimates for the sigma is unbiased. Okay. So anyway, we can easily estimate the mu's and sigmas, right? Because this is very straightforward and intuitive. And that is a simple demonstration uh, in terms of estimating a 1D Gaussian model. So far, we're very good, satisfied with the results, because given one distribution, uh, given the data drawn from one distribution, it's very easy to estimate the mu's and sigmas behind. Okay, we simply compute the mean values and the standard deviations, the variance. Okay, but I lay out all the logarithm, all the likelihood and the log likelihood functions, so that the whole procedure is described as a learning problem. Okay, we start by from some parameters that are unknown, and then we wish to find those parameters by learning from the data, following the principle to maximize the log likelihood. Okay, and that also explains why the intuitively reasonable uh, mean values and sample variance make sense. Okay, all right. Now, having solved the one Gaussian distribution, now we can probably look at the mixture of multiple Gaussians to let's look at how they look like. Okay, all right. So based on the assumption from the previous example, say the data can be from one Gaussian distribution, and then we can simply have multiple Gaussian distributions, which are defined by different mu's and sigmas respectively, right? We can have k Gaussian distributions, and each of those k distributions has its own mean values and sigmas. Okay, then how do we generate the data? That is the problem we want to ask. So given a data point, how it is generated from these multiple Gaussian distributions. Okay, so we consider this as a generative process. Say, given any data points, we need to first draw from the k distributions because we already have k distributions. We want to draw from k distributions with the probabilities, right? So not we assume that they are not equally probable, equally likely to be drawn from. Okay, and each distributions have the probability from Q1 to Qk. And after the distribution is selected, then suppose that the J's distribution, the J's Gaussian is chosen, then we need to draw a data from that distribution. Okay, and that distribution has this that yes, that distribution has this quantity, mu j and sigma j. Okay, so here we're talking about two separate steps. The first step is to decide which distribution to use. Okay, and but that process, this um, step is also determined by a bunch of prior probabilities from Q1 to Qk, okay, which is unknown at the beginning. And the second step is um, to narrow down to that selected distribution, which has its own parameter, mu j and sigma j. And then we draw one data point from that Gaussian distribution. Okay, and we are already familiar with one distributions because the PDF function for one distribution is defined as by this PDF function. Okay, so that is the overall two steps of dealing with generating one data points from a mixture of Gaussians. Okay, so it's basically a two-step thing. All right, now let's look at the example of two Gaussians. So now we have two kinds of fishes, right? Not just one kind. And we have salmon and tuna mixture together, okay? And if we plot them along the x-axis, it may look like this, right? Note that they are in the same color because we don't know the labels yet. We don't know which one is which. But in general, we can observe the two clusters, right? We can see that, okay, so a bunch of fish, the weight of them centered around this area, right? On the left area, and the others centered around this area, okay? So our task is to find the distributions that best describe these two clusters. So what is exactly the mu's? What are the values of the mu? Mu1 and mu2, and what is sigma 1 and sigma 2? So that these parameters can best describe this, can best fit these two, all the observed data points. Okay. So now, as we described before, a data point is generated according to this process. First, we need to select the fish kind, select the which kind of fish it is from, right? We use the phi s, okay, to describe the probability of that fish is from salmon, okay, and the phi of t being tuna, okay. So it is just the Q1 to Qk that we described two slides ago, okay. And these two probabilities sum up to one because there's only two possible outcomes, okay. They have to be normalized in this way. So that is the step one. And in step two, given the fish kind, then we need to generate one data point from the corresponding Gaussian distribution. So salmon has its own Gaussian distribution described by the, the mu of salmon and the mu of the sigma of salmon. Tuna also have its own distribution described by the tuna of the mean of tuna and the sigma of tuna. Okay, so it's two steps problem. Okay, so in order to model this problem with mathematics, we need to borrow some latent variables um, to help us model the whole process more properly. Okay. Now the parameters are here. Okay. The phi, the t, the mu, the sigmas. These are what we want to learn from the data, right? This is our goal. We want to estimate those parameters. Okay. So these two, the phi's, they are the parameters for the mixture probabilities, and those are the parameters for each Gaussian distribution. Okay. So because each data point we don't know if it is a salmon or tuna, we have to estimate it. So how do we do that? So we now will we will construct a latent variable, latent random variable, okay, which is called z, and di indicates which Gaussian distribution xi is from. Okay, so it's an additional random variable. Okay, so zi equals 1 is for salmon and zi equals 2 for tuna. That is our assumption. Okay, it can be also it can be other arbitrary values other than 1 and 2, but we use 1 and 2 for simplistic reason. Okay, so the likelihood of xi, it becomes like this. Okay, so it can be decomposed into a summation, right? Because zi has two possible outcomes, either 1 or 2. So the probability of the data points xi is actually the summation of two likelihoods. Okay, the likelihoods being salmon plus the likelihood being tuna. Okay, and now we will need to construct another notation, another variable called qi. So don't be afraid if it's too many variables coming out, because later on we're gonna eliminate most of those variables. But in order to help us formalize the problem, we need to use those variables like the capital Q. So let Qi to be the distribution of Zi, okay? So that's the Qi of Zi sum up to 1, okay? And the Qi function actually tells the probability of Zi belongs to one particular fish type, okay? So this Qi, you can think of it as a anonymous discrete function that's sum up to 1 for all possible outcomes, okay? So it is something that we conceptualize, okay, which does not exist in the before in the definition of the problem. Okay. All right. So now the problems becomes we can rewrite the likelihood of data points because it's a two-step problem because we need to first draw from the distribution qi to to tell which zi it is, and then we will use the likelihood divided by this qi based on the uh, uh, because we want to normalize these two terms, right? We will basically indicate decompose the likelihood within one possible outcome, right? With one term in the numerator and one term in the denominator. They basically eliminate each other. Okay, so we rewrite the likelihood. So I think the remaining slides here are okay. So this slide is something we still need to talk about. Okay, so the likelihood of the whole data sets becomes this, right? We um, put the products of the likelihoods into the product of this summation. Okay, so you can imagine a parenthesis along this summation because this is exactly how we represent the likelihood of one data point given all possible distributions that data point can be drawn from. Okay. Okay, so that is the rewrites of the likelihood and the log likelihood. As we did before, if we take the logarithm of this product, it becomes more complicated term. Okay, but don't worry, if we follow the principles of taking the um, derivatives of taking the logarithm functions, the product out there will becomes, excuse me, the product out there becomes a summation term because we take the logarithm of it, right? And also we put the logarithm inside each term of the summation. It's the logarithm of a summation, but this time we cannot eliminate the logarithm. It eliminates the summation here. The summation needs to exist because it's the logarithm of the summation. And luckily, we only have two options. We only have two possible outcomes. So we expand the summation uh, explicitly. So it's just the case of q z equals 1 plus the case of q z equals 2. Okay, it's either uh, salmon or fish, right? So this is a log likelihood. So remember that the log likelihood is something we want to maximize, right? It's the likelihood of the whole data set. So we need to maximize this log likelihood. That means we need to take the derivatives of this log likelihood, okay? But it is difficult to take the derivatives of this log likelihood, right? Because it's the logarithm of the summation of our parameters, okay? So here we will see some mathematical tricks because the original log likelihood is hard to um, take derivative of, and it's hard to solve all the parameters with analytical solutions. So the step we will take here is not maximizing the log likelihood itself, but we can maximize a lower bound of this log likelihood function. Okay, that means if we can find an expression E, and when we maximize this expression, and we also know that the log likelihood is always bigger than the E, then that means whenever E is maximized, then the log likelihood is also maximized. Okay, so I think it's a pretty advanced technique. So in the next few slides, I put all the I put an optional label on each slide, so it is optional. But I think I will go through it quickly so that you know how basically it works. Okay. And the principle of choosing this alternative expression E is that it should be easier to calculate derivatives than the original form of the log likelihood. Okay, so let's try to find the lower bound. That's here the original log likelihood is that it's the summation of the logarithm functions. And within the logarithm function, it's also the summation of two terms, right? Two weighted summations, q z equals 1 and q equals 2. Okay, so now we can think of these pretty complex terms, the probability terms, as simple forms such as a and b, right? So it's the logarithm of q equals 1 times a plus q equals 2 times b. Okay, so the q are probabilities, right? We use q's to describe the probabilities of all possible distributions, all possible Gaussians. So we'll let the a and b be two values of a random variable x. Okay, and then this q z equals 1 times a plus q z equals 2 times b is the definition of expectation, right? It's just expectation of a random variable x, right? So if it's the logarithm function, right, the logarithm is outside this expectation. So the logarithm of an expectation, right, the x-axis is the expectation. So the logarithm of expectation should be here, right? Because the expectation E of x should exist, should be within somewhere in the middle between A and B, okay? And the expectation, the logarithm of the expectation is also between the logarithm of B and the logarithm of A, okay? So if we draw a straight line here, then the expectation of the log, here I switch the order of the expectation of the log function. It should always below the logarithm of the expectation because the log function is a concave function, right? So convex function. So since the logarithm of the expectation is greater than the expectation of the logarithm by switching the order of the two functions, so we have found a lower bound, right? Our goal is to find the lower bound for the log likelihood function. So this can be the lower bound that we find. Okay, so now let's rewrite these these formulas. We move the logarithm inside the each summation term. So right, we move the log inside the a and the log inside outside the b, right? And this makes it easier because it's directly the log of these two probabilities. Okay, so remember this is the lower bound of the original log likelihood. Okay, and now we need to replace the Q with something we know, right? Q is something we invent, we create from nothing. So we wish to replace Q with some estimation. Okay, let's proceed on to the next slide. Okay, so this is the principle the trick we used is called the Jensen's inequality. Okay, whenever f is a convex function, we can use the expectation of that function as the lower bound for the function of the expectation of something. Okay, now we need to replace the q's with something we know. By something we know, we actually mean that it should be something that we can estimate or something we can observe from the data. Okay, so let's return to the meaning of the Q's. Q is the probability of one data point belongs to one cluster. Say it is a probability of one data point being salmon or being tuna, right? It is the prior probability we want to estimate. And it is something we can guess after we observe the xi, okay? For example, we can simply use a reasonable way to guess the probability, right? We can compare two quantities. Say, assume that, so it's actually a mind experiment here. So assume that one data point is from a salmon, right? Then we can compute the likelihood of X by this way. The likelihood of X is the probability of the prior probability of salmon times the conditional probability of xi given salmon, right? And the conditional probabilities is defined by the PDF function of the salmon's normal distribution, and the prior is our parameter phi s, right? So if it's a salmon, then we can have its likelihood like this. And similarly, if it's tuna, we can use another Gaussian distribution to estimate the likelihood, right? So now we can have two likelihoods, one for salmon and one for tuna, right? So because these are two quantities, we can always find a larger one, right? If the likelihood of being a tuna is higher, then it makes sense to say that, okay, it is more likely to from this data point is more likely to come from tuna, right? So the chance of xi being salmon, right? Notice that here the order of the probabilities, the order of the variables is switched. Okay, so it is the probability that these data points belongs to salmon is by taking this likelihood as the numerator and the summation of these two likelihood as the denominator, right? And to normalize the probability. And the other chance being tuna is to use the other likelihood. Oops. The other likelihood here as the numerator. And the same, actually the same denominator. It is a summation of two likelihood. Okay, so these probabilities are something we call the posterior probability, the probability of being salmon given that data points, and the probability being tuna given that data points. Okay, so these posteriors are what we will be used to estimate the Qs, to replace the unknown Qs, right? Because Q is something we that exists in our concepts. All right, but the posteriors are something we can observe actually from the data points. They are from the actual data points. All right, so now let's do the replace. Okay, so we are going to replace all the QIs here, right? All the QIs with the posteriors, WS, WS, WT, WT, right? And also, this is a inequality because this is the lower bound of the original log likelihood, and we write this explicit term as the log likelihood prime, because this is not the actual log likelihood, it's still the lower bound. Okay, but we are happy with it now because there's no annoying unknown variables, there's no Qs. Okay, and the remaining parts within the logarithm function, which is the likelihood of the data, can be replaced by the PDF function from a Gaussian, okay? So this term can be replaced by the Gaussian from salmon, and this term can be replaced by the PDF from tuna Gaussian, the Gaussian distribution of tuna, okay? So now everything are the known variables, are the known parameters. Nothing are the fake variables. Okay. So the derivative of this log likelihood prime is much easier to calculate than the original log likelihood. Okay. So what we can do is to take the derivatives of this log likelihood prime and make all the derivatives to 0 so that the maximum point is computed. And those maximum points will be the one that also maximize the original log likelihood. All right. Now let's proceed to the next one. So here I'm gonna proceed faster. So if you take derivatives of the mu s here, the mu s is the mean values for salmon, right? So the tuna terms are all gone because the tuna terms are constants relative to the salmon, right? And we will have this term to be 0. And we can solve it, which gives us the solution to the mu is like this. All right. It's the summation, weighted summation of all x, weighted by the posterior values of salmon, uh, divided by the summation of all the posteriors. Okay, we will analyze the meaning of this term later in the next slide. And for sigmas, we have this term to be 0, and we can also solve it. And it turns out that the sigma of salmon is also the weighted summation of all the variance around the mean of salmon, and weighted by also by the same denominator, which is the summation of all the posteriors. Okay, so we use the same weights, which is posterior. And similarly for mu of t and the sigma of t here. Okay, and we also need to solve the phi s and phi t, which are the prior probabilities for salmon and tuna. Okay, and if we take the derivatives of phi s and phi t, we have additional constraints because they need to sum up to 1. So we need to use a Lagrangian method by constructing a Lagrangian term, which is beta, right? Because this is a constraint optimization problem. So we need to use the beta times this transformed constraint here as the additional term in the Lagrangian. Okay, but this is also easy to compute because once we take derivative with respect to phi s, it's easy to find that phi s is like this and the phi of t is like this. So that means the negative beta is m. And we can substitute the m into the term for phi s and phi t. We can easily get the solutions. Okay, so we should be happy now because all of these solutions are obtained. Remember, we have 6 parameters: the mu for salmon, sigma for salmon, the prior probability for being salmon, the mu of tuna, sigma of tuna, and the prior probability of being tuna. We can have these parameters computed purely from data. So you may see that the WS's, right, the WS and the WTs, okay? So don't worry about the W's because the W's are also from the data. The W is the posterior the estimated posterior probability for each data point. Okay. So yeah, I listed the solutions for the W and the WS and WTs here. Okay, these are posterior probabilities, which are estimated to use the old values for phi S and phi T. Okay, so actually we are showing a iterative algorithm here. So what I listed within this dashed line box is something we need to repeatedly compute. Okay, we need to repeatedly update all the parameters, the phi's, the mu's, the sigmas. We need to repeat those steps until they don't change, until they converge. Okay, and this repeated algorithm is called repetitive algorithm or iterative algorithm is called EM method, which is short for expectation maximization algorithm. So I think we have some time for going through the 1D case for this EM algorithm. So assume that the data are from K distributions from phi 1 to phi K. So this is a more general case than the salmon versus tuna, right? We have K distributions. So we need to first randomly initialize all the parameters. We give them random values because we don't know any pattern at all in the data. Okay, and then we need to repeat two steps. The expectation step or the E step is that for each data point, we need to compute the expectation of which distribution it is from, defined by the posterior probability. Okay, so we need to compute the W of I for each J, which is the posterior probability estimated by this. Okay, and this P, the PDF function, is a well-defined PDF function from a normal distribution. Okay, so this is the E step. It computes all the expectations. And next comes the M step. The M step will need to use the expectations, the W's computed in the previous E step to update the parameters by maximizing the likelihood. Okay, so the new mu's will be the weighted summation of all the data points, but weighted by the mu of J, the W of J, normalized by the summation of all W of J's. And the sigmas will be the weighted summation of all variance, but weighted by W of J and normalized by the summation of W of J. And so is the phi of J, okay? And we do this for all the J values from 1 to K, okay? This is the so-called EM method, okay? So yeah, all these values are the weighted averages estimates for mu, for sigma, and for phi's. Okay, so let's first compare it because we mentioned that the EM, the clustering, so the mixture Gaussian method is different from k-means or from other traditional clustering methods, clustering algorithm, in a way that it assigns the probabilities. So let's see from the algorithm alone how it is different and how it is also similar. So for k-means, we also start with initialization, right? We initialize all the k centroids from mu1 to mu k. And we also repeat two steps. So we doesn't hurt to also call the first step in k-means the expectation step, which is that for each data point, we will assign it to the closest centroid. right? We need to find the closest centroid for each data point by finding the j's that has the closest distance from the data points. And also we have an M step, which is to update the positions of the centroids, right? And it is computed like this. We take all the uh, data points that belongs to this cluster J, right? So as analogy, we can see a very similar behavior of the two data points, of the two procedures, but the only difference is that um, the previous um, EM method for mixture of Gaussian, all the weights are continuous values. Okay, so these W's, those posterior probabilities, they are continuous, not 0 or 1. Okay, so all the mu's, sigmas, phi's, especially the phi's, they have continuous values. Rather than the k-means, they are actually discrete values. Like one data point can only belongs to one cluster. Okay, so I think our time has come to the end for today. So in the next lecture, we're gonna go through two examples showing how the mixture of Gaussian works. We're gonna use a one D dimension as the tuna versus salmon's example, and we also look at a simple 2D example here. All right, so that's so much for today. And if you have questions, let me know by email. And also a reminder that we have our last assignment due this weekend.